So orthonormal sets are good. So what happens now, and we'll consider, for example, just simply Rn. If you are given a basis orthonormal basis is better. So if I was given a basis that's not orthonormal, how can I make an orthonormal basis based upon the fact that you have a basis? You could always just simply throw on an orthonormal basis. But normally what I would rather do is take a basis and modify it accordingly until I get a new basis that's orthonormal. And so this idea was, if I was given, say, A, which is equal to A1, A2, up to AN, can I have a process where I'll get a Q, which is made of Q1, Q2, up to Qn, where this side is not orthonormal, and this side is orthonormal. What's this process? And this process is called the Gram-Schmidt Orthogonalization process. So if I have a bunch of vectors that are a basis, but they're not orthonormal, can I do something that I spit out another basis that is orthonormal, that every one of these column vectors are orthogonal to one another and they're all of length 1? And the process that we'll learn is the Gram-Schmidt orthogonalization process. All right, what's the idea? The idea is an inductive process. What's induction? Induction says we have a beginning, the basis, right, the first step. And then after that, we follow a pattern that is always the same sort of pattern. And the inductive process is based on exactly what we did up above, right? It's based on the least squares approximation, which is this. If you have a vector, let's say A, you have a subspace, which is simply going to be a span of, say, Q1, Q2, up to Qk, then if this is vector A and this is the span of Qk, I can actually find a projection, P. What's P? P is the part in the span. On the other hand, what am I looking for? I'm not looking for something in the span, which is what we wanted for the least squares problem. I'm wanting something that is what? Orthogonal to the span. Who's orthogonal?
A minus P.
A minus P. In other words, this problem says, the least squares problem says I'm interested in P. Well, P is easy to find. What is P? It was what? A constant times Q1 plus a constant times Q2 plus a constant times Qk, right? But what are each of those constants? So what is P really? What are each of those constants? It was the inner product between what? A and Q1, and then we'll have Q1 plus the inner product between A and Q2 times Q2, and we keep on going until we have the inner product of A and Qk times Qk. So I can still do the least squares problem. The least squares problem says, hey, what's in my subspace? Why do I know this is true? Because what are those? They're orthonormal. Since they are orthonormal, this is true. But what do I want? Normally on the least squares problem, you would stop. This is the thing in the subspace that you were trying to find. This problem is not interested in that. What I actually want is what? What's A minus P is what? That is orthogonal to Q1, Q2, up to Qk. In other words, this guy here, which is A minus P, that is my orthogonal complement. My problem is it's orthogonal, but I want orthonormal. So how do I make it length 1? Divide by its length. And so what I will do is I will keep my next guy, Qk plus 1, is going to be 1 divided by the length of A minus P times A minus P. It's exactly the least squares problem, but what I'm focusing on is this is the part I want. It's just the wrong length. So how do I find it? I find it by first finding the projection, which is found by the least squares technique, and then I subtract. I now find the orthogonal. I just need to stretch it. We're good. We found the next. So that's what we're going to do. What I actually showed you is the Gram-Schmidt process. So we need to build them up one at a time. So the Gram-Schmidt process does this thing one at a time. So the basis step, again, what is happening? A will go to Q. The basis step is to get the very first of the objects. Well, the very first of the objects is just going to be, I want Q1 to be, all I'm going to do is say, I don't care which direction I pick, so I'm just going to take A1, its first basis, and then divide it by its length. What have I done? I've taken A1 and made it a unit vector. And so Q1 is my very first of my orthogonal, orthonormal bases. I only have one of them. So its span is going to be 1, just one dimension. From here on out, we now do the inductive part. And what's the inductive part? The inductive part is we need to find projection P onto the span of Q1, Q2, up to Qk, right? The ones, this is really what I'm talking about, is up to the known Qs. So for here, the first time I run through the inductive part, Q2 is going to be based upon what? Just the span of Q1. And then after I do that, part B is we have the difference of find projection P, oops, forgot a word, of the next AK plus 1 onto. What are we projecting? It's the A, but what's the next A? That's our next A onto, and then we find their difference. Which is going to be A K plus 1 minus this projection. And then we keep the next next q k plus 1 is going to be 1 over a k plus 1 minus p times a k plus 1 minus p, which is exactly what I wrote before. So what would this algorithm as a process look like? So let's say I had, for example, A1, A2, A3, and A4. How would I generate Q1, Q2, Q3, and Q4? The way this process works is, step 1, Q1 is equal to 1 over the length of A1 times A1. So Q1 has been found. The next part is, so this was, I need to find Q1. The next part is, I need to find Q2. All right, this is where induction kicks in. All right, to find Q2 is, I am going to do this, I'm going to project A2 onto the span. And so I'm going to say, what is it? It's going to be, so we're going to have A2 onto the span of known. What's known? Only Q1. So that's just simply Q1. This is my knowns. What is that? How do I find the coefficient? I take A2 onto Q1, Q1. Remember how there's an ABC? That was the first thing we did. That's A. What's the B component? What's A2 minus that? Well, it's going to be A2 minus that. And then C is, what's Q2? It's going to be 1 over A2 minus the projection times A2 minus the projection. And what have I found? Q2. How do I find Q3? A. I'm going to take A3 onto span of what's known now. I know Q1 and I know Q2. So that projection is what? What's the least squares technique? It's the coordinates, which is A3 onto Q1, Q1 plus A3 onto Q2, Q2, which is some sort of vector, right? B, I take A3 minus P. C, Q3 is now 1 over the magnitude of that times that. I have now found Q3. See how this process just continues? What's the only thing as you look at this, and we would just continue this process, what's the only thing that's really changing each time? The least squares just keeps getting longer because we found more stuff. Right? We just keep projecting, and so there'll be one more term for Q3, there'll be one more term for Q4, there'll be one more term for Q5 as this thing keeps on going. All you'd have to do is plug in numbers and then grind this sucker out. Right? This is exactly the algorithm. Can you start to see how you would get reasonably good at doing these sort of projections? And then you would have an orthonormal. Now, if you would keep track of the following, if I would keep track of everything that I circle, that one, that one, that one, if you keep track of the coordinates upon the projection and then the scaling of the making it into a unit vector, right? So every time you go through this process, if you keep track of the scaling and the coordinates of the span, the scaling and the coordinates of the span, you can actually take each of those these right here, and we can give them their own name. If I would call this guy, say, R11, and I would call this one R22, and this one R33, and I would call this one R12, and I would call this one R13, and I would call this one R23, and we would continue that process. So the 1, 1, 2, 2, 3, 3 are tracking just the stretchings. And the R, if I look at this, what's R12? R12 is I've taken A2 and projected it onto the Q1. What's R13? I've taken A3 and projected it onto Q1. I've taken A3 and projected it onto 2. If you do this and then store it as capital R, which would be R11, R12, R13, and if this was 3 by 3, instead of like, I suppose, I did a 4 up here, if I would knock off those 4s, so we only had those 3. And then this would be 0, and this would be R22, R23, 0, 0, R33. It would end up being that what you actually found was A is equal to Q times R. If you would multiply these back out, what you've really done is say, hey, if I multiply, if we look at it, you can sit there and say the projection here, like this, gets you back to the Q3. And so I have this many Q3s, this many Q1s, this many Q2s. Multiply all those out, what are you going to find? A3. And so this is the orthogonal component of it. And so what you do is say, hey, what is A3? A3 is this on the span, which is that vector right there, and this in the orthogonal complement, which is this vector right here, which is this multiplication of that. And that's just A3. And so if you would multiply this all out, it ends up being that A is actually Q times R. So when you do the Gram-Schmidt process, not only do you go from a basis to an orthonormal basis, you've actually factored A. So not only is this a orthogonalization, this is also called QR factorization. So by Gram-Schmidt, we have factored A into A equal QR, except what's Q?
The orthonormal basis.
This is orthonormal, right? It's an orthonormal basis. What do we call such a matrix? A matrix whose all of its columns are orthonormal bases. It's an orthogonal matrix. And R is what? Upper triangular. Remember how we've already done one factorization, LU, lower triangularization and upper triangularization, and we did that to be able to do things like solving Gauss-Jordan, right? On the other hand, if I go ahead and do a Gram-Schmidt on this and I make a QR, that actually ends up being that, so if this is true, if we could actually do this, so why would I want, why am I interested in a QR factorization? If I have to do, can you actually look at this? How many think you could go ahead and write the code for this? The pseudocode's actually in the textbook. You can go through it. So it wouldn't be that hard, right? Just simply just go through here, inner product. What's the inner product? It's a scalar product, right? So you just have to have a scalar product, and you can make a QR factorizer. So we could actually do this. It seems like kind of a process. Why is QR interesting? Well, what would happen if I said solve AX equals B, and it was solvable? Normally we would do, find the inverse, move it to the other side. Well, if you had A as QR, then solve AX equals B is really solve QRX equals B. Now when I look at it, I'd like to move Q to the other side.
Oh, yeah.
But moving Q to the other side means I need to find what?
The inverse.
It's inverse. But wait a second. It's orthogonal.
The transpose.
And so because Q's inverse is just simply Q transpose, that's really easy to find, that means Rx is simply Q transpose B. You look at that and say, well, what's the point? Well, this is upper triangular. And if you have an upper triangular matrix, solving it is just simply back solve. You don't have to move it, right? You know what the bottom solution is because since it's triangular, the bottom equation is linear, right? It's just z equals this number. Well, if that z equals that number, get rid of all the z's. But then you've reduced it to, y is this number. Oh, I know y. Let's get rid of all the y's. Oh, then x is this number we solve. And so because this is upper triangular, we can just simply immediately solve by back substitution. So there's nothing to actually do that's computationally difficult because you've already done the work by the QR factorization. And so, okay, I don't have to find the inverse. I don't do anything else. Just make a QR, move the Q just by taking its transpose, and then just simply back solve immediately, and you've solved it. But this is obviously computationally costly. And there's lots of solving these problems. You solve by Gaussian elimination with back solve, Gauss-Jordan, which is the inverse, which gets you the solution, QR factorization solving, there's LU factorization solving. You move through all of these different techniques because certain matrices blow up with certain techniques, and other matrices work with other techniques. I mean, the question is because certain groups of numbers don't, because they're numbers and they're approximates, certain algorithms are just problematic. For these, if you have these numbers, this one's bad. Use this one. Oh, these numbers, this one's bad. Use the other one. And so you kind of play around a little bit. But it's just a technique to solve. And it's nice. And also you get an orthonormal basis, which now, this particular technique would work with any inner product space because is anything that I wrote here dependent upon Rn? No. So I could do the same sort of thing, with any inner product space. We could find orthonormal stuff within any inner product space. Now, that's 5. We're not supposed to do 5.7, so that's the Gram-Schmidt. Certain things that you should read because it'd be nice to have this been a 5-hour class and we would actually go through all of the entire book instead of just simply the 3-hour class. Certain ones that would be very, very useful. One, Gram-Schmidt is something that you can do by hand, but they have what's called the modified Gram-Schmidt process. You ought to read that because Gram-Schmidt by hand is something you can do. When you try to code it, it actually blows up because of errors. What happens is you constantly project. The problem is this. The Q1 you found due to numeric approximation is a little bit wrong. But if it's a little bit wrong, it's span a little bit wrong, which means this is a little bit wrong, which means Q1 and Q2 are a little bit off. But now their span's off, which means Q3 is now pointed in a little bit more of a wrong direction. But now 1, 2, and 3 are in a little bit wrong direction, which makes Q4 even in a worse direction. And so there is a way that you can modify this to make it a little bit more computationally stable as you're doing wrong numbers. Because the numbers that you plug into it are always wrong, right? The other is read 5.7. This is, it's not a requirement, but the thing is that most of the stuff we do is project upon polynomials. And 5.7 covers a bunch of orthonormal polynomials over vector spaces with their own particular inner product that are used for different reasons. And a lot of these ones have applications, so you might as well look through it and say, they're all the same thing. We're projecting upon these orthonormals. We do the same stuff. We just use a different inner product and pick different orthonormal polynomials for particular applications. And so they kind of go back and forth. And so they have different classic ones that you'll run into a lot of times. You know, Legendre, Chebyshev, Jacobi, Hermitian, Lagrange, and then it talks about using particular ones for integration versus other ones. And so, anyways, they're all same idea. All right, that's it.